Hi everybody, how we doing? As it turns out, if you joined us from our last little meeting, I did not make it to Tampa because I think it snowed every time since we last had an opportunity to chat. So I'm here, ready to help out however I can. It's going to be an exciting session for me because I love math. So I've always really loved math. And I don't want to spoil my question for you tonight, but I have a PhD in mathematics. And my question for you, just as a warm up, I want to hear what the chat thinks about this, is on a 0 to 10 scale, what would you say your feelings are, just your general sentiment about mathematics? 0 to 10, what do you think? Okay, we got some 10s. I know the suck-ups when I see them. That's okay. A very honest 3. I like that. Generally a lot of 6s and 7s, all right. Not too surprised by that. Yeah, we should do math for lovers. I agree with that. Maybe we can do something like that coming soon. One of my big frustrations with math is I think that a lot of the way in which math is taught is not really what math people do on a day-to-day basis. And so there's this divide between, well, you certainly learn a lot of arithmetic and methods and these sorts of things. You learn a lot of mathematical algorithms for performing computations. But you don't actually get at the soul of what mathematics is. So in starting this course with some ancient Greek mathematics, the idea is to kind of get at that soul a little bit. And we're going to do a very brief warm-up here before we get started. Before we start, though, one thing I did want to remind you of is if you are interested in a certificate, as a reminder, we have our practice exercises for everything that we're doing in this first chapter of material. We're nearly through what I'm calling Chapter 0, and we're going to see today why I'm calling this material Chapter 0. And there are tons of exercises here, so everything from, we start off with permutations and combination functions, and then we move towards actually some unsolved or unresolved mathematical questions about numbers that we don't actually have clear-cut answers to. And these exercises are not trying to get you to solve the questions, but to explore how we might find these numbers that often are these very large numbers, and we don't know, for example, are there infinitely many of them, or how long does this pattern go on, et cetera, et cetera. And so the questions here on our practice exercises are a lot of like getting you comfortable to do some practice with the types of things that we've started with at the foundations of Python, but also allowing you to explore these types of mathematical questions that you might not be that familiar with. And as a reminder, you may or may not know this, but I've dropped a link in the chat to sign up for where the autograders live, where you can test your progress and get a certificate. And as I've said before, we also have all these check your work exercises. So we're going to explore some GCD algorithms in this stream, and there's an opportunity to check your work from what we do. So as you code along, you get a little bit of credit just for completing those exercises too. All right. I like math when applied to science. I do too. That's part of the reason there that I kind of made the transition towards computational biology, because I had no idea when I started off getting interested in mathematics that there were compelling, interesting quantitative and computational questions that you could address with mathematics in biology. I always thought it was just a lot of memorization. And I like a lot of people, I had not the best biology class, but from my perspective, I finally kind of made this transition towards biology. And if you are a 6 or below on math, I'm hoping maybe I can move you a notch or two up in your own scoring system with what we're going to do. let's get started soon. If you're just joining us for the first time, welcome. We got lots of links in our description. So there's links to join our mailing list, hop on our Discord, even get membership in Philomath if you want to explore deeper, or get office hours, or just support what we're doing. And if I see a lot of familiar names in the chat, which is awesome. So if you're a return guest, welcome back. And let's head towards getting started. So I want to ask one question though, which is especially for the folks who I want to maybe hear from the 9s and the 10s here, which is, my question is, who has that one good Euclid GCD algorithm explanation? And what I mean by that, and there's an explanation of this on our Programming for Lovers website. That's our final important resource. But there is this notion that if you have two numbers, two integers I should say, a and b, and let's say that a is bigger than b, that the GCD, meaning the greatest common divisor of a and b, is the same thing as the GCD of a minus b and b. So I dropped a link to that, or a description of that algorithm in the chat, or equation I should say, in the chat. Does anybody have a short explanation of why that equation, like when a is bigger than b, the GCD of a and b is the same thing as the GCD of a minus b and b? Why would that be true? Why would that be true? Can anybody give us an explanation for why such a thing might be true? What do we think? The chat has gone silent. I love it. If anything, this is a great explanation for what I'm seeing, which is a lot of the problem with math is how it's taught. Sometimes that's the teacher, sometimes it's the curricula. But what we're going to rely on is, what you're going to see is an algorithm for computing a GCD that is based off of this equation. And I'm going to show it here momentarily. And the bigger picture question that we're going to look at is why do we care? Like why are we, what we're going to look at is an algorithm for computing this GCD that is very old, over 2 millennia old, from Euclid. Why does it matter? Like, aren't computers fast? Why does it matter which approach we use for computing a GCD of two numbers if we need to do this? And then the other thing you might wonder is, why do we care about GCDs? And the reason, as you're going to see, is what we do is indicative of a huge number of things that happen anytime we're studying algorithms. I have an approach, you have an approach, we're going to compare them. How do we know that my approach is faster, your approach is faster? How can we quantify that? All right, this is great. We don't have a good short explanation. So I'll give you a very high level explanation. This is an example of something that we see in math, which is, if I want to prove something, establish that I know something is true, sometimes you can establish a more general fact is true. So let me give you an example of what I mean here. Here's your little glimpse into math. If I want to say this equation, the greatest common divisor of a and b is equal to the greatest common divisor of a minus b and b, I also could do something that's more general, which is to say, what if I show all of the divisors of a and b are the same as all of the divisors of a minus b and b? Not the greatest common divisor, but all of the common divisors. So if something is shared by one of the two pairs, it's shared by the other. And now that seems like a more complicated question. But I want you to think, say for example that you know a number is a divisor of a and b. And if you need like a specific collection of numbers in your head, think about like 3 is a divisor of both 9 and 15, right? So it's a shared divisor of those two numbers. Now when you subtract the larger number from the smaller number, what happens? You get 15 minus 9, which is equal to 6. You had two numbers that were divisible by 3. If you subtract them, that resulting number, which I was calling a minus b, still divisible by 3. 3 is a divisor of that new number as well. So anytime you have a divisor that's shared by A and B, that is also a divisor of A minus B. I could write that out as a very formal proof. I don't think I need to do that, but the idea is nevertheless the same. Think about a specific example, and that'll help you see that this is true in general. All right. So then the other question, though, is we need to say what happens in the reverse direction. Meaning, if a number is a divisor of A minus B and B, is it true that it's a divisor of A and B? And I want you to think about, well, the same case arises. 3 was a divisor of 6 and 9. You add those two numbers together, right? And then you're going to get 9 and 15. So adding or subtracting the numbers from each other is not going to change the fact that a number is a divisor of them, right? And so as a result, again, that's a high-level explanation. But what that insight does is it allows us to power an algorithm for computing a GCD, which is based off of this fact that the sets of divisors, the collections of divisors that are shared for those two pairs of numbers have to be the same. This is an old observation, but then one that's very useful and that I will be able to show you in a very modern programming language tonight. So that's where I would like to start, which is let's see Euclid's GCD approach and put it into a modern context and compare it against a simpler approach and see if it really is worth the bother of studying. And to do that, I'm going to go into my source code directory. And I'm going to create a new folder, and let's call it GCD. And in that new folder, I'm going to create a file called main.py. And let me get some starter code. So I've been going into hello and getting some starter code and putting it into main.py. And here, instead of hello world, we're going to say studying GCD algorithms. The other thing you might notice is now that we've reached this point, we've identified, we've done enough to be able to understand what's going on with this extra 2 lines of code here that's at the bottom of the code. That I said essentially just means we're going to run whatever is in main. When we run the code via the command line and we say python3 main.py, what happens is this name variable, this is a variable that has a reserved name to it, it gets set equal to this string. So behind the scenes, if you want to say, has the user tried to run this code, then this is going to be true. And now when this is true, we're going to enter this if statement, and all this line does is say execute main. Main is a function, and what is contained in the main function is everything that we see here. So now we have a little bit more context about what these two magic lines do that just say essentially, run this code. But that's just a little bit of context about what's going on. So in the meantime, we want to study these GCD algorithms. And I am going to copy over a little bit of pseudocode. So if you follow our explanation of all of this on our Programming for Lovers website, we explain it in a way that is language neutral. So it's not with respect to any particular language, so we can kind of convey what are the high-level ideas that are being presented here. And I'm just going to put all of this into triple quotes, so it's going to be read as a comment and not be read as code. And I'm going to point out we have 2 algorithms here, the trivial GCD and Euclid's approach. And we're going to walk through the implementation of each of these now and see how this goes. We're going to start with the trivial approach. And what's nice is this might be the approach that you would come up with if you were going to try and compute the GCD of 2 numbers by hand. You'd say, well, why don't I just try every possibility? So I could set, for example, some number d equal to 1, and then I'm going to try every possible divisor up to some point. And I think it's not hard to see that that point should be the minimum of the 2 numbers. And we could get more clever than that, but we can go up to the minimum of the 2 numbers and then say, is the current number that I'm looking at, is it a shared divisor? And if so, I'm going to update this special variable d that I'm using to store that largest number. Then at the end of that process, I'm going to return d. So I will put all of that into a function. And my function is going to be called trivial GCD. And as we've seen before, we're going to make sure that we have this nice focus on style where we have type hints and where we use docstrings. And so I will say we're going to look at A and B. So A is an integer and B is an integer. And what this is going to return is, of course, an integer. And then we're going to make sure that we have our docstring. And this docstring will say, well, what are we doing? We're returning the greatest common divisor of two input integers using a trivial algorithm that tries every possible divisor of A and B. And our parameters are going to be A and B. I'll say A is an int, and B is also an int, and then we're going to return an integer, which is the GCD of A and B. Okay. And now if we look at our code, what I probably should do is let's have this adjacent to the code that I'm writing. Okay. This is the idea. And the idea is that we're going to set an initial variable d equal to 1. It's going to be our first, where the variable is going to start. So if these two, in other words, if A and B are what's called relatively prime, they don't share any divisors in common. Imagine a number like 4 and 9. Those two numbers are not divisible by anything other than 1. And so we want to return that value when we strike out and when we don't get any results at the end. So I will use this d to store our first try at this. And if we never update d, that's fine. We'll just return d at the end. And then we're going to say, well, we need to do a couple things. So I need to know how far up to go. And in order to do that, we could say m is equal to the minimum of A and B. And that's a function that we've already written, that minimum function that takes the minimum of two integers. So I could do one of two things, actually do three things. I could import this function from where we've already written it. We're going to talk more about import statements later. I don't think we need that right now. So I could go in and I could grab it from where it's written. I could copy it over. So this was when we looked at conditionals. We had this min2 function, and I could go into conditionals and I could find def min2, and I could copy this code over. Probably the simplest thing to do, though, is at this point to let you know there is a min function that's built into Python, and it's okay to just use that. We don't have to write our own code for something that's what is a relatively straightforward and built-in task. So once we have m is equal to the minimum, what we'll do is we'll try every possible divisor or candidate divisor up to and including m, and update d every time we find a divisor. So this is the idea of what we were presenting. And now we're going to get to use what we learned about previously, which is if I want to do something a bunch of times, what am I going to need? This is a loop process. And then in particular, I know exactly what condition I want to apply. So I want to do this for every possible candidate divisor that I'm going to be called p. For p in a range of numbers. And it's nice that Python gives us this notion that I can have a loop that says we're going to range from 1 to, and we want to go up to and including m. So here's where we need to make sure that we appreciate how does the range function work. Python's going to adopt a very standard modern convention, which is to go up to m plus 1. So the second element there in the range is going to tell us one pass where we're looking. And if it's the case that p is a divisor of both, then d should be equal to p. And here's where we need to say, all right, how can we test this? For one, and you can get ahead of yourselves, you can think, I need to test two things, right? I need to test, is it a divisor of A? I also need to test, is P a divisor of B? But before I even get to that, I need to say, how do I check? So first, here's a good question for the chat. How do I check, is P a divisor of A? Right? How would I make that check? And good question from Claudia in the meantime. Do we need to import min? Do I need to import range? Because you see they've lit up their yellow. They're both, in a sense, functions, right? So since they're not in our code, maybe we need to import them from elsewhere. Good point. They're so fundamental that they're just built into Python, so you don't have to import them from anywhere in particular. Great. Everybody's seeing the way to check if a number is a divisor of another number is to say what happens when you take the remainder when the division occurs. And if that remainder is equal to 0, well, then you know that it's a divisor. So I can check if P is a divisor of A by saying if A, and we've got the remainder operation, which is represented as the percent symbol. So if A percent P is equal to 0. So in this case, we say it's a divisor of A. And I can enter the if block. Now I say, well, what do I do now? I need to check, is it a divisor of B as well? So if B percent P is equal to 0, then we can say it's a divisor of B. And now we can say if both of these have occurred, if I'm inside of this innermost if block, then it must be the case that P is a divisor of both. And I can safely update D to be equal to whatever the value of P currently is. Good. Now the question there is, how can I make that like a little better? Have we learned any like habit, you might say, about programming that we can apply here that might make our work a little bit easier? If you know me, there's something I don't particularly like. Good. So some folks are saying, look, what I'm trying to test is two things. I'm trying to test, is it a divisor of A and is it a divisor of B? And what I don't like is nesting things too much. So you notice we've got a for and then an if, and then we're inside of this if and then another if. And generally, whenever you see this, just as a rule, what you're going to find is there's probably a better way of doing it. We're going to talk about that in other contexts, but for now what I'm going to say is here's our opportunity to use this and keyword. And so if the and of these two statements is true, then we know that P is a divisor of both. And I can simply update D to be equal to P. And now we have this nice tight test for P being a divisor of both these integers. All right. Now, the next question I would say is, why don't we run this? Okay, so we've got, this is a nice short algorithm, and we could call this function in main. And one of the things we might do is to set two hypothetical variables. I won't call them A and B. I could. I'm going to call them x equal to 63 and y equal to 42. And the GCD of these two things, I would hope, will be 21, because 21 is a divisor of both, and it's the largest one. So let's see what happens. The GCD of 42 and 63 is, and let's call trivial GCD of 63 and 42. Okay, and now we're ready to run our code. So we're going to create a pull up the bottom ribbon, bring up a terminal. We should be getting comfortable with this at this point, I would hope, which is to say I know that my File Explorer is bringing up the Python folder. So I just need to navigate to the src source code directory. And within that, I need to go to this GCD folder. And so that's going to point us at this folder containing main.py. And because I'm on a Mac, I can make sure that my code is saved. And then I'm going to run Python 3 main.py. As always, if you're on a Windows machine, it's just Python main.py. And I'll run it. And fortunately, we see that the GCD of 42 and 63 is indeed 21. All's right with the world so far. We can run additional tests on this if we like, but for now it's good enough to say it appears to be working. Now here's a quick question though, which is, say hypothetically, I want you to just think about, this is a focus on control flow and thinking your way through functions and what's going on here. What happens if, we set D, we set M, and we start P at 1, and I'll have you note, we don't have to start P at 1. There's one tiny little improvement we could make, which is to set this equal to 2, because 1 is a divisor of everything. We've already kind of established that with D equal to 1. So I'll make it a little bit faster with this check. But I want you to imagine what happens, say P is equal to 2, and we enter this, and we're checking that P is a divisor against A, and A is, let's say, an odd number. So let's say A is equal to 63. That's a good odd number. And in that particular case, this statement is not true because 63% 2 is 1 and not 0. So this test, and I could even parenthesize this, I don't have to, but for the sake of clarity, this might look a little prettier. This test is going to be false. So if this is false, here's my question for you. What happens to this entire statement? What happens? Okay, Robert says it's false. Okay. There's a stronger answer here. Yeah, Tal, I like that. Get out immediately. That's hopefully you're not talking about me and my house, but you mean the code. All right. If this statement is false, there's no way that this whole thing can be true. There's no way that P can be a divisor of both A and B if we've already established that it's not a divisor of A. So this is just an aside to say this is called short circuiting. And so I'll just add a little comment here, which is to say if the first statement in an and is false, then the whole thing is immediately false. And the second condition isn't even read. This is something that's pretty standard among a lot of programming languages. But Python's like, I don't even need to pay attention to it. So you could put something that winds up causing an error over here. And as long as this is false, it's just going to ignore it. That's something that's worth knowing. We also, you might imagine, if you want to test, are both of these things true? Well, we also have an OR statement. And so I'm going to show, because I'm a math person, I have to show you the and the or truth tables because these are useful for computing as well, but they all stem from logic also. And I'm just going to put these in a bunch of comments. So I'm going to imagine that we have two statements. We have like an X and a Y. They're Boolean statements. So they take a true or a false value. And what I'm going to say is, we have all these possibilities. We have X and Y and X or Y, and there's 4 possible outcomes. So they could both be true. And if they're both true, then we know that the evaluation of X and Y is going to be equal to true. And I'm just going to do and first. So if X is true and Y is false, then X and Y is false. And so in general, if you're trying to establish that the and of two things, both of them have to be true in order for X and Y to be true. Otherwise, it's going to be false. So in either of these two other possibilities where X is false and Y is true, or they're both false, the X and Y proposition, we might say to be fancy, is always going to be false. We also have a built-in keyword of or, though, which is going to say X or Y is true if at least one of the two statements of X and Y happens to be true. So if they're both true, X or Y is true. And if just one of them is true, well, X or Y is true as well. We haven't used this so much yet, but we will. And the only time here that X or Y will be false is, well, if they're both false. And here would be an opportunity for me to ask you a quick question. which is there a short circuit for X or Y? So when would Python short circuit and say, I don't need to make the next check. I don't need to check the second statement. If I have X or Y, when is it I'll be able to say immediately, I know what X or Y, the truthiness of it. Is it true or false? So when would I be able to make that immediate conclusion? So if the first statement, which I'm calling X, is true, X or Y short circuits to true. So we know it immediately must be true. And that's because if X is true regardless of what Y is, you're always going to be true. All right, great. Worth knowing. One more thing I want to point out, another opportunity for the chat here, okay, is to say, what if I did something like replace this statement with or? Okay, so if I'm going to introduce or, here's an opportunity to say, well, this is not going to be right, but what actually would happen in this algorithm if I replace this with an or? What would this function return? I mean, there's a chance that the output might be really hard to understand. That's one possible answer. Also, but maybe it gives us something that's predictable. And if it's predictable, what is that thing? Okay, some good thoughts. Return the greatest divisor of one of the numbers. What's the greatest divisor of a number? Like 63. That's an easy one because that's just 63. So if you think about, let's think about our for loop. I might say, what's the last time that D gets updated? Well, the last value of this is M. M is the minimum of A and B. Okay. Is M going to be a divisor of A or B? I would think so. So think about specific numbers here. I gave you 63 and 42 before. What's the minimum? It's 42. Okay, well, then we're going to range up to 42. And the last thing that we check is going to be 42. All right, well, let's say B was 42. Is it the case that 42% 42 is equal to 0? Yes, very much. When you divide a number by itself, you get a remainder of 0. So just as a quick quiz to make sure we're on the same page, that's what would happen if this were an or. Fortunately, it's not. Fortunately, it's an and all is going to be right with the world. One other thing I want to point out, actually I'll say a couple more quick things before we move on. One thing that we might do is to say, well, let me point out one thing, which is it is very tempting, especially because Python looks a lot like human languages. Why a lot of people come to Python and find it attractive. It kind of looks natural, like 4p in range, 2 to n plus 1. Very natural to forget about something like this statement here, and to just have code that looks like this. If a%p and b%p equal to 0, this is the kind of thing to be wary of. So I want you to think about if you have an and of two statements, so this will get read as an error. If you have an and of two statements, it needs to be an and of two separate statements, like things that we can evaluate as true or false. And this is something here that is evaluatable as true or false, but a%p doesn't make any sense. That's just an integer. So make sure that we're always, and if you need help with this, you can always parenthesize the two expressions or multiple expressions that you're joining with and or. The other thing I wanted to say is what would happen if, though, like somebody put in the wrong values into trivial GCD and they said, you know, I tried to plug in like a negative number into trivial GCD. Then what we might say is I don't want to allow the user to be able to do that. So what we will do is to say, I'm going to check what's going to happen if somebody tries to plug in if a negative number for A or a negative number for B. And I can check that too. So for example, here's an opportunity for us to use or. And we could say like if a is less than 0 or b is less than 0. Okay, and again, I could parenthesize this. There's nothing wrong with this. You probably lose these over time. But I could establish these as the two things that I'm trying to check. If either of those two things is true, I want to get out of here. And I'm going to say, I can check this. Again, this is a focus on style to say, I can assert that these values are appropriate. And in this particular case, I can produce an error by saying raise. This is a value error because the value of the parameters is not within allowable ranges. And I'm going to say this takes a string, and I'll just type in an error, and then what happened? A negative input was given to the function. Okay, and this test needs to happen straight away, like at the beginning of the function, so we don't harm anything by trying to do something in the meantime. All right. That is trivial GCD, and it's quite a lot to say, but we had some focus on style and make sure that we understand how or and are working. But what we really want to implement is this other algorithm, which is Euclid GCD. And I've got my pseudocode here for all the pseudocode fans. And we're going to have a very similar algorithm, or similar algorithm in terms of the high level of it. It's going to return a GCD, but it's going to do something very different to get that GCD. Now we have some questions. I like that. What about, yeah, okay, sure. What should this be, less than or equal to 0 or less than or equal to 0? Hang on to that thought. I'm going to go ahead and add them for now for you. That's good. I like it. Hang on though. In the meantime, I want to say, let's do the same thing for Euclid. So I'm actually going to just copy over this entire part of the function. Let's do the whole thing. Okay. Because the only thing I really need to change is to say, I'm looking at Euclid GCD. The input parameters are still two integers, still returning an integer, still performing this test, and I'm going to say this is using Euclid's algorithm. Okay. Now, we then need to run, or actually implement the algorithm itself. And here's where we use the critical fact, which is that the GCD of A and B is equal to the GCD of A minus B, and B when A is greater than B. So in layman's terms, if you want the GCD of two numbers, just subtract the smaller one from the bigger one and replace that number. And then the idea here is you can just keep doing it. Once you've made those two numbers smaller, so say in the example of, what did we have? We had 63 and 42. Subtract 63 minus 42, and that gives you 21. And now you have the GCD of 42 and 21. Subtract 21 from 42. So now you have the GCD of 21 and 21. So I even show this. GCD of 63 and 42 is equal to GCD of 21 and 42, which is equal to the GCD of 21 and 21. And when you have the GCD of two numbers that are the same, you don't have to be so good at math to say the GCD of those numbers is equal to itself. It's equal to 21. So we're going to apply this, and you'll notice this is an extendable idea, right? That I can just keep doing this. Anytime in programming, we think, well, I'm going to keep doing something for as long as something is true. The word loop should be going off in our head. So that's the idea of how the pseudocode representation of this algorithm is going to work. We're going to say, while it's the case that these two numbers are not equal, subtract the smaller one from the bigger one. And that's handled by these two cases. So I'm going to convert this idea to Python. I'm going to say, while it's the case, here we get to use our not equal to comparison. So while A is not equal to B, it's tempting to say, well, just subtract A minus B, but this is true when A is greater than B. So we need to have two cases. So we have two cases, depending on whether A is bigger than B or B is bigger than A. We know that A is not equal to B because we're in the while loop. So if we're in here, we know that they're not equal. first thing we're going to do is to check, is it the case that a is greater than b? And if so, I'm going to update a to be equal to a minus b. So I'm going to subtract the smaller number from the bigger one and update it. That's what we were doing here. Okay, so we said 63 was bigger, 42 was smaller, replace the bigger one with the difference. Else, so we know that b is greater than a, and we're going to apply the same trick. So b is bigger, so b is going to get updated to the value that it currently contains minus a. At the end of this whole process, what do we know if we're here? It's a good question to think about. Once I make it here, I know something has to be true. Something has to be true. What is that thing? Good. A is equal to b. A is b. So we started as a not equal to b. This thing is going to keep going forever. It could actually be an infinite loop for all we know, until it's the case that a is equal to b. So we know if we're here, it's not the case that a is not equal to b. So you have two nots. And so we know that, well, a is equal to b. So if they're equal, well, we know what their GCD is going to be. It's just going to be itself, like this case here of GCD of 21 and 21. So I'm going to say return. Now, do we return a or do we return b? But here's the case, well, we're not returning the variable, we're just returning the value. And what do we know? They're the same. So you can return a, or if you like b's, return b. Doesn't matter, either one, because they're the same. And that's Euclid's algorithm. It's somehow even shorter than this approach that you might like teach to a child, which is to just try every possibility. Now we want to time the two algorithms and see, do we care? Because it might just be the case that this like interesting idea, I hope I've at least convinced you that this is of interest, because this is a lot different from this first approach. But do we care? And so the question becomes, how is it that we could time the algorithms? But unfortunately, the math people called, right? And they said, well, we have definitions for GCDs of like negative numbers. So if I were going to say, whatever the GCD of negative 63 and 42 is, it's also equal to 21. It's defined, it has to be positive, but this negative number, it still has divisors. So just because it's negative doesn't mean it's not worthy of having divisors. So thank you, math people. Okay, great. So that means I need to handle what happens if either of these numbers is negative, and I'll handle it in both of the algorithms. So our raising a value error is not fair to these negative numbers. And then the question becomes, well, what should I do, right? How do I fix this? And I want you to think, my hint is contained here. I have a nice compliment in the chat that I've been doing a lot of abs, which is true. That's true. I don't know how you can tell, but I have been doing a lot of abs. Oh, absolute value. I see. Yes. So yeah, that's one way we could get around here. And yes, Python has a lot of built-in stuff. We have take the absolute value of both inputs and replace them. So yeah, that would be a nice little clever thing we could do. A equals the absolute value of A and B equals the absolute value of B. So then we're just saying if it's negative, it's going to get its absolute value. That's completely fine. I would say let's replace this with, I think probably some might say a clunkier thing to do, but something that I think is just as good. And it doesn't assume that you know that there's an absolute value function built in or remember this. if a is less than 0, just replace a with negative a. That's essentially all that's happening anyway. And if b is less than 0, less than negative, we're going to say b is equal to negative b. Okay, so you're just going to update those values to be their negatives, which is going to make them positive. So if you have negative values, then flip their signs. Okay, and we'll do the same thing down below. And now I can get rid of this. And I'm going to add this as our check here. Instead of raising a value error, we're going to look at value errors more later. And that's going to handle that. One thing I want you to make sure that you're aware of here is it would be very tempting to do this as an else if. But remember, we use an else if in a very specific case. An else if is used in the particular case that I want to test like multiple different things. So I have like 6 cases I want to test. So I have an if and an else if and an else if and an else if. This is not that case. These are 2 completely independent cases that we're checking A and we're checking B. They don't depend on each other at all. And so the last thing I want to do is say, oh, A was not less than 0. So essentially this particular statement is only going to apply if we skip this statement. So if it were the case that they're both negative, you'd actually miss this, which is not good. And so because you've already entered this. So else if only gets checked if this is not true. And that's not what we want at all. We have 2 independent tests, and that's why we use if instead of else if. Minor point, but it would cause a bug. And now we're good to go. Now we're good to go. Except the math people are going to call back. And what are the math people going to say? And this is, I'm telling this as a math story, but it's a story about making sure that you're being thorough. When you say, I've got parameters, those parameters could have values. I need to make sure that I'm handling anything that could happen. What are we missing? What if there's 0? So I had that before. You made sure that I handled that case before, but now I've got this case of what happens if there's 0. And the math people are going to say, they're going to tell us that the GCD of 0 and n is going to be equal to n. Okay, and this is the type of thing that makes other things work out. So it's like, I mean, it doesn't really have a grand explanation that's perfect to make you understand that the GCD of 0 and n is equal to n. It just kind of, it makes other things nice. So certainly, I guess n is the divisor of 0 because you could multiply it by 0. So fair enough, GCD of n, 0 and n is n if n is greater than 0. So maybe I just, for the sake of clarity, say something like that. All right, now this means I can make this check and say, how do I fix this? And so I'm going to say, well, I'll say, if it's the case that a is equal to 0, what do I want to return? Well, I said GCD of 0 and anything is just that thing, and so I'm going to return b. And then we're going to say if b is equal to 0, we're going to return a. Right. So that will handle this case of the fact that the GCD of 0 and anything is equal to 0 to n. And now John has a good question because he's becoming a math guy in real time. This is great because he said, what about GCD of 0 and 0? But they already told us what that should be, which is 0. Okay. And so GCD of 0 is 0 is 0. And here we say we finally made them satisfied, but we've handled every case. And you say, how do I know that I've handled 0 and 0? Well, if a is 0, I'll return the other one. And if b is 0, then that still returns 0 and we're okay. So I'll say this works even if they're both 0. And now everybody is satisfied. But even with something like this, which I'm going to add to both algorithms, add it to Euclid, and I'm going to add it down here to the trivial algorithm too, just to make sure that everything is okay. It's still fraught with peril because I could have put these two checks, I could have switched them, and it'd be so easy to say, oh, I don't like this 0 case. I'm going to check that first. And so what would be the problem with this? Does anybody see? This actually, even though it looks perfectly reasonable, this would incorporate a bug, which is what? What is our bug here? Okay, what if non-integers? Absolutely. And we could get into, so one of the things that when we introduced variables, we talked about types. And there are actually ways of, we could call the type of a variable and we can check what that is. That's great. And there is no end to the number of things once we go down that rabbit hole of realizing that good code often has a bunch of these checks. But there is a case, even when they're integers, of something that could go wrong. Good, which is what would happen if like B was negative? A was 0 and B is negative. Then you go, A is 0, B is negative, so I'm going to return B. But B is a negative number, and so we don't want to return any negative numbers for GCDs. We'd want to return negative B. So we have to handle the negative cases first, and then we handle the 0 cases, and then we can do the algorithm that we care about. Okay, so we need to make sure that the negative cases happen first, and then the zeros, and then the regular algorithm. Okay, and fortunately, the math people called back and they say, thank you for caring about how we feel. And you're finally ready to do what you wanted to do, Philip, which is to show what happens when we run these algorithms. One thing I probably should definitely do is just to convince you that the Euclid GCD algorithm appears to be working. So let's do that. Let's go into main. Let's go into main and say, wherever main happened to be, and say we have this, and then let's just replace this with Euclid GCD, make sure everything is good, and open our terminal, and even if we call Euclid GCD, we see it's 21. It's indicative of actually a way of testing. If you have two algorithms for something, you often want to run a bunch of tests, but you can run the tests and make sure that they're giving you the same outputs on the same inputs. That's one way of making sure that two algorithms seem to be working. Good. And now we can do what we want to do, which is time them. So again, why do we care, right? There was a lot of instructive about looking at these algorithms, and how to handle cases and all that stuff. But at the end of the day, we're computing a greatest common divisor. Computers are fast, right? Like, what do we actually care about? Euclid's approach for computing a GCD versus a trivial approach. Presumably, they're both very fast. So let's see. What I'm going to do in main is I'm going to show you how to time algorithms. Regardless of if you're looking at mathematical algorithms or whatever, it's often very useful to time algorithms or components of functions so that you can see how long something is taking. So what I'm going to do is, first at the very top of my code, and I think it's safe to get rid of my pseudocode now, I'm going to import a package called time. So this time module, I should say, in Python, is going to have a bunch of functions for identifying like the current time. And we're going to use these functions as like a stopwatch of sorts. So I'm going to show you how to do it. If we go to main, what we're going to do is to say, let's establish two numbers and let's make them, I'm going to make them reasonably big. So I'm going to say like X, they're on the order of 1,000,000. And I have two numbers that, I have in mind, and I realized I didn't even call X and Y here. I just called 63 and 42. I don't need X and Y, but I do need X and Y now, which is to say, let's say 3782026, and Y is going to be 2731479. All right. So these are our two numbers. There's nothing special about them. They're just two numbers on the order of 1,000,000, meaning they're in the millions, but they're not in the 10 millions. And let's time the trivial approach. So I'm going to say, how do I do that? I'm going to say there's a variable that's going to be equal to the current time. And I will set start is equal to time dot time. And that's not the most attractive code in the world, but it means go into this time module, and there is a function in that time module called time. So that's what we're calling with the parentheses there. And this just accesses the current time. So I want you to think about what's happening here is this starts a stopwatch, so to speak, like a virtual stopwatch. And so we know at this point in time what the time is, and it's in this variable called start. What is its type? Its type is a time object. No reason for us to think deeply about that for right now. And then I want to call the algorithm. That's what I want to do. So I want to call trivial GCD of x and y. And you'll notice, but that returns something. So we need to say d equal to trivial GCD of x and y. And one of the nice things about Python or a lot of languages is if you don't actually care about the output, you don't have to put it anywhere. So I'm just going to call the function. And when I just call the function has run, and now it's complete. And so I'm going to stop the watch by saying there is another variable that accesses the current time, and I take the difference between it and what the time was at the start. So it just works out that you can just think of these as integers, or not integers, but say decimals, storing the amount, whatever the time was at this point, maybe in the number of nanoseconds since the Big Bang, I don't know. But however you're keeping time, the total amount of time this thing took is the difference between what the time is now and the time was at the start. So this stops the watch. Okay. And what we want to do is we're going to print the time in a pretty way. And we're going to do this quite a few times as you follow the course with us. This is a common thing that we're going to do to say how long is this algorithm taking. Soon we're going to do the same thing for like prime number finding algorithms, but we're going to do other things as well. And so to print something in a pretty way, we're going to use what's called an F string, which says I will format this string in a nice way if I put F and then the string that I care about. And the string that I care about is to print to the console something nice to the user. So I'm going to say that the trivial GCD function took, and what I want to print is a variable, and that variable is elapsed. And so I'm going to put elapsed into braces, and then I'm going to say seconds. So that's how this elapsed variable is being stored. It's in seconds. And I can be a little more precise too by saying I want it to like 6 decimal places, so I can say colon dot 6f. That's just an indication that I'm going to store it in this the decimal in this particular way. And now I can run that. So I can save it. I can go to the console. I can retype python3 main.py or hit up, hit enter, and it'll tell us trivial GCD took 0.05729 seconds or 259 seconds. Pretty fast. I like that. All right. And John says, if only I could import time, and he's gotten that share song stuck in my head now officially for like probably 3 or 4 days. So thank you, John, for that. In the meantime, what I actually want to do is do the same thing for Euclid. And I want you to start thinking about, say I do this for Euclid. How much faster is Euclid going to be on these two numbers? Do you think it's going to be about the same amount of time? Do you think it'll be substantially faster? I mean, this is pretty quick. This is like the blink of an eye, right? 1/20th of a second. That's not very long at all. So it was able to compute 2 reasonably big numbers. What do we think? And then the question becomes, how do I even compare these two things? I guess I could take the difference. In my case, I have an MBA, which if you've joined us since the beginning, this is probably a world record for the longest anybody with an MBA has taken to tell you that they have an MBA. So congratulations to me. However, one of the things that they teach you like 4 or 5 things, just like over and over again. One of them is if you're interested in 2 things, and they both seem like good information, you can get promoted if you just divide the two things, and then that helps you measure them. So in this particular case, that's what I'm interested in doing. I want to say we're going to have like the same exact thing. I can even use the same variable. So I'm going to say start equals time.time. And then I'm going to say, let's run Euclid GCD of x and y. And then we're going to have elapsed, except in this particular case, I'm going to call it elapsed 2 because it's a different value, is time.time minus start. So start the watch, run the algorithm, stop the watch. And now I'm going to say Euclid GCD is going to be the same thing. Okay, so I'm going to say how long did Euclid GCD take? Be very careful to make sure that you call that elapsed 2. I guess technically in Python, they'd want an underscore there. So I could save this and I could run it. But I'll give you the fancy term, which is where we have two numbers here, and we're going to divide them in order to tell us, what is it that, how do we compare one versus the other? And this is a fancy term. It's called the speed up, provided by an algorithm. Algorithm 1 compared to algorithm 2 is the ratio of the runtime of algorithm 2 to algorithm 1. Okay, so I'll print that speed up value as well. And we've got like sample values here. And I want, just as a question, right? We've got two numbers on the order of about 2-3 million. I ran Euclid and I ran trivial GCD. What do you think the speed up provided is going to be? Like, it's going to be a number. And so this is the slower algorithm, hopefully that's trivial GCD, divided by the faster algorithm. So for example, if algorithm 2 takes 8 seconds and algorithm 1 takes 2 seconds, the speed up is 4x. Okay, why? Because I divided 8 by 2. So give me, for this particular case, before you run it, give me a hypothetical number for what you think the speed up is going to be. The speed up needs to be, I would hope, positive, because we're taking the slower thing, the longer thing, and dividing it over the shorter one. In the meantime, I'm going to say we're going to need an F string. And we're going to say that the speed up here is the value that we care about. Okay, and this is going to be x faster. I'm going to put the x over here. And what I care about here is the speed up variable, and I should tell you what that is. The speed up variable is just going to be elapsed divided by elapsed 2. And I could get really fancy, I guess, and I could say this is elapsed Euclid, and this is elapsed trivial, and I need to update this to be elapsed trivial, and this is going to be elapsed Euclid. Okay, so I'm just making this a little bit better in terms of style, just to say this is going to be elapsed trivial divided by elapsed Euclid. Okay, and then we're ready to print it, except I'm going to say, let's print it to 2 decimal places. So I'm going to say :2f. Meanwhile, the chat has a lot of thoughts. Okay, so we have a million. We have 1 over 1218 or 1 over 1,000, which I assume you mean it's 1,000x speed up. Infinity, I guess that could be the case if it finished in 0 time. So maybe I'd have a check to say, how much time did it actually take? All good thoughts, because we don't know yet, right? So let's run it. We're going to save this, and we're going to run it. Let's see what happens. Right. So Euclid GCD took this amount of time. Trivial GCD took 0.05 seconds. And the speed up here is 3183, which is pretty good. That's impressive. And I see in the chat there's already ideas for what we should do now. Like you're saying, well, Well, how did you pick these numbers? Well, we should probably pick different numbers. And then the question is, what numbers should we pick now, right? We've got two numbers that are like 2 and 3 million. What's the next thing that we should do? Try larger numbers. You know, we might even do something else, which is to try smaller numbers too. But we should try numbers that are a little bit different, okay? So I could just chop a value off these and then run the algorithms again. But what I want you to tell me is, what do you think is going to happen when we run these algorithms again with these slightly smaller input sizes? What do you think will happen this time? I'm going to get ready to run it. So they'll both run faster. But then remember, we want the promotion. We care about the speed up. That's really how we measure things, because the speed up allows us to measure any two algorithms. It doesn't matter how long they take. It gives us this nice simple ratio. Same speed up? More? Let's see. So when we run it this time, the speed up goes down. So the trivial GCD took about 10% as long as it did before. The Euclid GCD algorithm actually took about the same amount of time. So the speed up here is only 244x. Before it was nearly 3200x. So what does that mean if I keep adding digits? Okay, so I made values where I added a 6 and a 9, and now let's add two other numbers. Let's add a 2 there and a 0 there. What do you think happens to the speed up now? Well, it got smaller when we made the numbers smaller. When I save it this time and I run it again, the speed up now goes to 23,000x. And notice that Euclid is still taking about the same amount of time. So Euclid is at 0.000023 seconds. So even though we've added a factor of 10 essentially to the numbers, the trivial GCD algorithm is taking longer and longer, but Euclid is taking about the same amount of time. And then what's going to happen when I add another one? Add a 1 there and a 7 there. So at this point in time, we have 9-digit numbers, and we could run it. And this, now I'm going to have to wait, because trivial GCD is getting slow. At this point in time, it takes nearly 6 seconds to run on my computer. Euclid GCD is still lightning fast, but the speed up is now like nearly 300,000x. This is making, it's two simple algorithms. And I want you to appreciate a couple things, which is, number one, this is really cool. Euclid's algorithm is worth studying. And here is, like, we can see it in front of us, that it's producing the speed up that is, I think, pretty surprising. But it's making a very deep point, actually, about algorithms in general, which is often an algorithm isn't, like, you're comparing two algorithms. It's not just that algorithm 1 is faster than algorithm 2. Great. It's that the larger the input data size, algorithm 1 speeds up compared to algorithm 2. And so a lot of times when you study algorithms, what you see is it actually doesn't really matter too much, or an algorithm might be slower. And then you need big data, large input data sets, and then algorithm 1 starts getting way better than algorithm 2. So algorithm 2's runtime really goes up. Algorithm 1 does not go up by as much, and so that speed up continues to improve. And the even deeper point is, this is why algorithms are more relevant today than they've ever been, because what's happened to data? We've gotten more and more data. We're drowning in data. Okay, 10 years ago, you could use the term big data, and that would be your way of just getting a nice 6-figure job. But it doesn't make it false, right? It's still a true statement. that the amount of data that we have has exploded. And this means that the study of algorithms is just as relevant as it's ever been, because as the data size increases, a lot of times when you improve an algorithm, it becomes more and more relevant as the size of that input data set gets bigger and bigger. That's my key point about why we care about algorithms. Now, the math people might call, and I've seen this point in the chat, and we're not done with GCDs. I want to move on to primes. I would love to get to primes. But we're not done with GCDs, because the question might be, well, we're doing a lot of subtractions. Okay, so there's one other thing to see here, which is if I just come down outside of main, actually I had some statements up here. Okay, say that you're looking at, I don't know, A equal to 50 and B equal to 375. So if you were going to do like GCD of 50 and 375, right? Then what does Euclid do? He keeps subtracting. And what he actually would do wouldn't necessarily be this. But I guess I should have a comment there. So this is equal to GCD of 50 and 275. And then he keeps subtracting. And we get to 50 and 225. I don't really think it's going to be tremendously instructive for me to keep typing this out, but what's going to happen when we get to the end, we're going to say that this is equal to GCD of 50 and 25. And so when we get all the way down there, what we're going to see is, couldn't I have gotten here a lot faster? Like, was there a reason to do all these subtractions? What could we have done? What could we have done instead? With these two numbers. Where did that 25 come from? What is repeated subtraction? Repeated subtraction is just division. So actually what we've done here, if we keep subtracting this number, we've actually divided 375 by 50, except that this thing is not 375 divided by 50. It's what happens when you do that division, then you take the remainder. So really what we had here is that this is equal to the GCD of 50 and 375% 50, which is equal to 25. So the rule really should be not to subtract the things, but to take our modulo operator. So if we want to be clever, we could say, let's do Euclid GCD faster, or faster Euclid GCD. It's going to do basically the same thing. We need to be a little careful. So we're going to have A as an integer and B as an integer, and that's going to go to an integer. And I'm going to say we're basically doing all of the same stuff here. So I'm still going to have my doc string. Okay. And our algorithm is going to say, don't just subtract. But one of the things that I want to point out is to really understand how to write this code. And this is for the precocious, but we delved into the realm of math people today, so we're going to see it all the way through. What's the next step that we have? So we have that the GCD of 50 and 25 is equal to the GCD of, well, you want to say you don't subtract them. We say 50% 25 and 25. And 50% 25 is just the remainder. When you divide 50 by 25, you get 2 with a remainder of 0. And so now you say, well, this is GCD of 0 of 25. And what's the GCD of 0 and 25? Now we have to remember. Not a trick question. 25. We said the GCD of 0 in anything is n. So our steps here are a little bit different. We've written this out to say, aren't you glad the math people called us? Because they said GCD of 0. Otherwise, we would have gotten to this point and said, this was a good idea. It was a good idea, but then we got down to GCD of 0 and something, and I don't know what that is. But now they called us at 25. Hey, that's the answer. This is going to work in general. So what we're going to say is, here's our algorithm that I've called faster Euclid GCD. We're still going to need the checks at the start, which is to replace with the absolute value. Okay, so we'll still do this. Still want to flip them, so we can assume that everybody here is non-negative. Okay, but then we need a very precise check. And so we're going to keep going. For how long? Like, till what? We're going to have a while something. But then what is that something, right? And that something needs to say, well, until one of them is equal to 0, we're going to keep going. When we hit the 0 condition, then we're good. We can just trust the math people. They're going to tell us, oh, it's whatever the number is. So we're going to keep going for as long as it's the case that a is not equal to 0. But they both have to be not equal to 0. So we get to use our and say b is not equal to 0 too. And we're just going to keep on going for as long as both those things are true. And we're going to say, all right, well, now we have two cases. It's just like Euclid. Which of the two things are we in? Is a greater than b or is b greater than a? And we're going to do the same thing. So if a is greater than b, well, I want to say a is equal to a percent b. That's where we had before. We said a equals a minus b. And now the only thing I'm doing is I'm replacing that with saying a equal to a percent b. Else, I'm going to say b is equal to b percent a. All right. And you might say, well, it's not necessarily the case that b is greater than a. It could be b. What's going to happen here is b is greater than or equal to a. But that's okay. If they're equal, I'm going to still divide them and take the remainder. Like if you had GCD of 25 and 25, well, you'd take the remainder when you divide them, and you'd have 0 and 25, and that'd give you 25 again. So you'd be okay in that case too. That's a technicality, but it's worth me saying. So we're going to keep going for as long as, well, they're both non-zero. So if we make it here, it's the same type of question I asked at the start. What is true if we make it here? Well, we know that we've finished with the while loop. So either a or b is 0. They might both be 0. And now we are in the realm of the dreaded mathematicians who tell us, well, if one of them's 0, just tell me the other thing. So if a is equal to 0, we're going to return b. And otherwise, I'm going to say, well, b is equal to 0. Because one of them's got to be 0. If a is not 0, b is. And I'm going to return a. And now this function is complete. It's the same general idea, but we had to be a little careful because it did change a little bit in terms of what our while condition needed to be. All right, so what is there to do? Now the only thing left to do is to say, we had this clever idea. We noticed repeated subtraction could be replaced by division. So let's go in and go to our main function and perform this timing. So we need to say we've done this part of it, and here's where copying some code is going to be really helpful, right? Like I could say we've done this comparison. Let's say we've got this. Let's start the watch again. Okay, I just copied all that down. Just want to be very clear here. So I'm going to say start the watch. I'm going to call, what did I call this? Faster Euclid GCD of x and y. See, And because I have everything installed in terms of packages, extensions for VS Code, I actually got that function suggested to me, which is nice. We'll see that a lot. And I'm going to say elapsed faster Euclid is the time currently minus the start. And I'm going to print how long did faster Euclid take. Okay. It took this amount of time. And then we can see what we're going to have. Except the speed up that I care about at this point in time is going to be, okay, well, we think that this faster algorithm is going to be the bottom. And so the slower algorithm now is not going to be trivial. It's going to be just regular old elapsed Euclid. So the only thing that I'm doing here is to say we're running the Euclid algorithm against this speed up that we have of it. And then the question is, in this particular case, what is it that you think the speed up will be? Okay, so I've got two numbers. They're on the order in the hundreds of millions. And the only thing I need to do is I need to be a little bit careful here. I guess I can run all of this, it doesn't matter, but I am going to have, the code's going to be a little slow because in this particular case, this is the speed up of Euclid versus trivial. And this is the speed up of fast Euclid versus normal Euclid. Before I run it, and you can go ahead and run and find out, but how much faster do you think it's going to be? What do you think? I mean, originally, this first implementation of Euclid, which just used subtraction, was like, could be hundreds of thousands of times faster on this data set size, is what we saw here. What about on this? For this case, what do we think? 32, it's an oddly specific number, great. Have we checked it's working? I mean, sure, we should probably check it's working. Yeah, that's a good idea. Let's double check. Faster Euclid GCD can go there. Hopefully that's 21. This is not the most robust testing. Let's see. So GCD of 42 and 63 is 21. Old slow trivial algorithm is taking forever. So speed up of Euclid versus trivial was this, which is 200-some thousand times faster. And in this case, normal Euclid is slower than fast Euclid. And we see it's probably on your computer, it's somewhere on the order of like 10 times faster. So probably, and I think I saw this point made, if I were to greatly change like the orders of magnitudes of these numbers, maybe that will change what we see. That might be worth running. So if I were to say, can always bring this back, but 2713, for example, you have a wide range in these two numbers. Let's see, we might want to run this a lot of different times. And so in this particular case, here is where you might see something quite a bit different. Euclid's algorithm in this particular case winds up being slower because this number is small. So Euclid winds up having to do a lot of subtractions. And here is where it winds up getting beaten a lot by the fast approach, which is not doing repeated subtraction after subtraction. You're kind of beating your head against the wall by subtracting 2713 from this number. You're going to do a lot of subtractions there. So that as a result, this normal initial Euclid algorithm that we produced doesn't work so great in these particular cases and does get beaten by the approach that takes the modulus. That having been said, what's the bigger improvement, right? It is important that we have the actually math algorithm, but the bigger improvement is not doing the percent sign. It's the original insight that when you take the GCD of A and B, it's the same as the GCD of A minus B and B. That's Euclid's insight, and it easily extends into this. Well, you can make it a percent, right? But that doesn't change a lot. Like either way, it's very beautiful. And it just happens to be that you need to improve it a little bit over just the raw subtraction if your order of magnitude of the two numbers is very different. But I think the lesson is that the elegant or beautiful idea is what really gives us the speed up. And the technical thing here is just the add-on optimization to make everything work out. And that's GCDs. So yeah, if you made it this far with me, congratulations. That's as interesting as I can make greatest common divisors. But I think nevertheless, even if you started as a 6 out of 10 on math, maybe you're like a 6.2. Like, where are we now in terms of math? What's your starting number and ending number? Did I bump it up a 0.4, a 0.5? Hopefully, all right? And there's a lot more where this came from. The problem is that we need people like more foundational education, because a lot of the really cool stuff too, you just can't explain because it gets quite complicated. 5 to 7, that's good. I'll take that. All right, give us another hour, we can get you to a 9. So we need to do primes. And primes are just as cool. I love primes. We're going to look at prime numbers. We're going to do the same thing. We're going to say, here's the simple approach to figuring out what prime numbers are. Here's the elegant, beautiful way of coming up with prime numbers that the person who discovered that the ancient Greek person who discovered the world was round and computed the circumference of the earth, also gave us a way to do prime numbers. So we're going to look at that too. The issue, though, is that in order to work with prime numbers, primes are like we're storing all of the things up to a point. And up to this point, we haven't done anything like that. We're just saying, here's a number, here's another number, we're going to get this number, and we're working with one variable at a time, or maybe a couple of variables at a time. What we need to do is collect a lot of things in one place. And when we do that in programming, that's what we call an array. Now, Python is fancy, so they don't use the term array. A lot of languages use the term array, but that's really what we're thinking of. So there's a second part here to what we're going to do. It's going to make our stream probably one of the longer ones of what we're going to work on. But we need to work with arrays and see the basics of it so that when we talk about prime numbers next time, it won't be very long and we can focus on just the timing, just implementing these algorithms, and just doing some things like visualizing these things, visualizing the primes. What does it even mean to visualize the primes? We'll talk about more about that here when we see the primes. But for now, I need to talk a little bit about how is it that we work with arrays. Okay. So to work with arrays, I need to create a folder. And I'm going to call my folder just arrays. And this is going to be, it needs to go in src. Okay. And this is going to be called arrays. And then I need a main.py in there, or whatever.py. And here's our code. And I'm just going to have my starter code. And my starter code I can just get from hello. And just put this here. And I'm going to say arrays in Python. And when we talk about, for now I can just minimize this. When we talk about arrays in Python, I'm going to say, well, we mean these are called tuples and lists. So there's two different ways that Python's going to allow you to store multiple things all in one place. And so what we want to do is I'm going to show you both of these. So there are two ways. The first way, the easy way, probably the easiest way, is to say if I know the numbers that I care about in advance, and I know how many things are going in this container, I'm going to use what's called a tuple. So tuples are useful if we know the values in advance. So what is a tuple? Like, for example, say I want to say the primes is 2, 3, 5, 9, and 11. We know that we at this point in time, imagine we figured out these are the five prime numbers. And I can say those are my primes, and I can print this thing. And so the tuple is always going to get enclosed in parentheses. So I can save this, and I could trash my console, bring up another one. I don't know why it does that, but we're going to cd into src arrays, and then I'm going to Python 3 main.py. And we say 2, 3, 5, 9, and 11. Okay. And we've seen tuples before. We had this when we first looked at functions. We had this double and duplicate function. So I said we had this simple function, and if you've done all of this, take a deep breath, pat yourself on the back. We made it a long way. Here's a function that like takes a float as an input and it returns 2 copies of it. And I said if you return 2 copies, you need this tuple of 2 floats. So it's a very brief introduction to it. But in this particular case, we've seen tuples before, and there's a rule here, which is that tuples, this is a word that if you join us, and I saw some questions, when we're going to see some science, we got to have the math first. Math is like the central thing to all of the science, and then the science can flow from that. So we have to do math. It turns out math is kind of useful if we're going to do like a gravity simulator, because, well, you're going to wind up with some formulas. And the same thing, though, which might be more surprising if you're going to do like evolutionary tree construction. It turns out that's like all math. That's been nothing but math people for like 50 years making evolutionary trees. So we're going to need that. But now all the math people that have gone from a 5 to a 7 out of 10 on how they feel about math, they've all told me all of a sudden they're math geniuses, and they know that 9 is not prime. So the fancy term in Python is that tuples are what's called immutable, right? And the root word there is that they cannot be changed. So we have this road to Damascus moment where we realize that 9 is not prime. Oh no. So let's change it, okay? And tuples are what is called zero indexed. We're going to see this like a million times. What that means is I start counting them at 0. So I'd say this is element 0, this is element 1, this is element 2, and this is element 3. So I could go in and I could access primes of 3, and I could say change it to 7. Okay. But the problem is if I save this and then I run it, I get an error. And it's because a tuple does not support item assignment. So you can't change, I'll just say, this will not work. Because you can't change individual elements of a tuple. Won't work, right? So tuples are useful, but you can't append to them, and you can't change individual elements. So if you have a bunch of things, they're not modifiable. The fancy term is they're immutable. So most of the time, some of the time we will, but most of the time we will use lists in Python. Okay, and there's a lot of different ways of declaring a list. I'm going to show you a few. So you could say like an empty list if you want to say has nothing in it, and I'm going to call that list empty list. I'll set it equal to brackets. And I could say, because it's Python, there's a million ways of doing this. So I could say it's equal to a list with parentheses. Doesn't matter. You don't have to know all the different ways of doing stuff. And so sometimes we want an empty list. Like if we don't know how big something's going to be, and when we look at prime numbers, that's a great example. I don't know how many primes there are up to a certain point. So I'll just create an empty list, and then I'll just keep adding every time I find a new prime. So there's a lot of applications that we're going to see. I don't know how big this needs to be in advance. Sometimes I do. So sometimes I just want a bunch of values that I set the list to. And the expression brackets of whatever that value is times the length is going to give you n copies. So we say n is equal to 6, for example, and a is equal to 0 times 6. Okay, so this would give you a list that's just 6 zeros. Nice and convenient. Fraught with peril. Okay, so we're going to see later on in the class that this is one of a lot of things in Python where it's like, oh, this is nice, I wanted 6 zeros. And then when you try to use this in other contexts, like total nightmares start happening and demons start raining from the sky. So more on my Python frustrations later. For now, I want to say, even if you're going to make a list, like a Python doesn't care. Like if I have a small list, let's make a small list. Let's make list. Let's make a small list, and it can even have different types. So in a lot of languages, you would try to do something like mixed list is equal to, we got a bunch of different values. You could have like 1, 3.14, negative 42, Python stinks, true, okay? So you could do all these different things. And in a lot of languages, like a hand would come out of the computer and slap you in the face. But in Python, this is totally fine. Like, I don't know, there's not a lot of context for, well, there's a couple contexts, but if you're a beginner programmer, there's not a lot of context you would care about something like this. So it's an example of, well, maybe the language should be a little more demanding, because why would you be doing this? But it's okay with it. And I'll show you, like we should print all these things. So I got an empty list, I've got I've got mixed lists. So let's print all of these just so you can see what gets printed. And we've got mixed list here. And I can save and I can run, and you can see all this stuff gets printed. So there was our first tuple, our mistaken primes tuple. There was empty list. Here's A with its 6 zeros that I created up here. And then here's our mixed list with a bunch of different things in it. Okay. Now, as I said, in Python, arrays, meaning tuples, or also lists, are lists use zero-based indexing. Okay, so the indices range from 0 to n-1, where n is the length of the list, the number of elements. Okay, so for example, if I wanted to set the first element of this list A, I could say A is 0 is equal to 8 or negative 8. Okay, doesn't matter what I set. And I could also set things with arithmetical formulas. So this is the first element. But I could also set like A of, I don't know, 2 times, let's set some variables here. Let's say like I is equal to 3 and K is equal to 4. And I could do A of 2 times I minus 4 is equal to K integer division 2, and then raise that thing to the 4 and add 1 to it, okay? And that's like, looks complicated, but it's just the same arithmetic stuff that we've been doing before. So you have 2 times 3 minus 4 is 2, and so this is the same as like setting A of 2 is equal to 4 integer division by 2 is 2. Raised to the 4th power is 16, plus 1 is 17. So it's like setting A of 2 is equal to 17. And the other thing I would say is length of A gives the number of elements in the list A. Okay, so that's a useful thing to have. And here's my opportunity to ask you a question, which is, how do I set the final element or refer to the final element of a list? In general, like for this particular list A, well, this is 0, 1, 2, 3, 4, 5. How do I get that last one? Okay, there's a couple of answers, right? A couple of good answers. We need to find the length of the list. 2 answers. I'm going to point to both of them. So the elements range from 0 to length of A minus 1. So if you have 6 elements, they range from 0, 1, 2, 3, 4, 5. We've already kind of seen this with, well, I looked at the range function. But in general, the element indices of a list, so the index just means which number are we looking at. So we go 0, 1, 2, 3, 4, and then we go up to length of A minus 1. So if I want to set the last one, I could say A of length of A minus 1 is equal to 43. And that works. So what's nice about that is it works for any old list. I don't need to figure out what the length is and then enter that as a number. And that just sets the last element. And now I can print all these updated values. So I'll say print A is now, and then I can print A, and you'll see all those values that got set. So after I changed those things, I set the initial one to -8, I set A of 2 to 17, and I set the final element to 43. You see they all got updated. So nice, good, okay. Lists are immutable. That's a good thing. So these operations which didn't work for tuples will now work for lists. Python also has a different way of doing it though. So the chat is wise. There's a different way of doing this as well, which is that I could just get rid of length of A. And we could say A of -1 is equal to 43. So if you see a negative symbol here, then there is a hidden length of A. It's like they're just saying it, so you don't have to type out length of A. Python is going to hold your hand and say you can just have the -1. It's okay. If you give me a negative number, I assume that you mean length of A of -1 there. So I could get, for example, I could get A of -2. You know, this is the penultimate element. A of -3 is the antepenultimate, I think. Third from the end, okay, and so forth. So all of this would be allowed because there's this hidden length of A lurking right there. Okay. So this is called negative indexing. And I'm just going to replace this here for now. And I'm going to copy this down and just have a little index for us that says A of -1 is the last element of A. Okay. More on that momentarily. One of the things I will say, you could be the best programmer like in the entire world and know Python and never use this. So there's one thing I want to point out is a lot of times there's all these bells and whistles and tricks in Python. And it's like sometimes they can be cool. This is kind of neat. And you're thinking, what's the harm in this? What's the harm in setting A of -1 is just A of length of A -1. That's fine. That's a nice little shortcut. It's cool. It's neat. All right, hang on to that for a second. But the point is, you don't need to know that in order to be strong at programming. One of the things I hope you take from this course is that if you're learning to program in Python, you can do one thing well, and that's just as good as knowing how to do a million things well, because it gives you a lot of ways of doing it. So the question here is, though, how far back do we go? This goes back how far? What's the final thing? A of negative what? This would be the first element of A. What goes there? 1, 2, 3, 4. How many things are there? And you could count. If you had 10 elements, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In general, you're just going to go A of negative length of A. So this is called negative indexing. And I'll say, ignore it if you want. I don't care. You can know this, you can not, but it's worth making sure that you see it. And I'm going to explain why you have to know, you have to have at least seen it for a moment. All right. Now then the question becomes, what happens? I like that the chat thinks it's cool. If I moved you from a 5 to a 7 in math, my central goal of my being is to move you from a that's cool to this is awful in like 5 minutes. So just sit tight. If I can get one person to realize that negative indexing is horrible, we'll be good. But for now, I want to say, what happens if you give it Python something weird? Okay. So for example, like by weird, I mean out of bounds. So I know that the length of, like to set the last element, I want to set it equal A of length of A -1 equals 7. That would set the last element. But say I forgot. one of the easiest beginner errors to make is to forget, oh, it's 0 indexed. Oh, the last element has to be at a of length of a. Or if you wanted to set the first element, I don't know why you would do this, but you did something like this. You went too far back. You went to negative length of a and then you subtracted 1. So you'd be too far back. What would happen if you did either of these? Well, if you try to save this, you're going to see you get list assignment index out of range there. And if I comment that out and do it again, you get it here as well. Okay, so this is worth knowing. If you go outside, indices outside the range from negative length of a to length of a minus 1, produce very common, very dreaded index errors. Should capitalize it. So that's a very common type of issue that you will see if you program a lot in Python. Sometimes we all make index errors. You just make fewer of them as you go. Now, hold on to negative indexing just for a moment. I want to show you what we want to do with using lists in functions. The whole point of this is not so we understand negative indexing, it's so that we can work with functions. So for example, I'm going to have a function called factorial array. And it's going to say, I want to produce a list of integers. So if I think about the type int, it's going to take an integer n as input. It's going to produce a list of integers. And let me give it a doc string. So I'm going to say produces a list of all factorials. And I think I have, make sure for the case of consistency here, I don't know what I'm doing. I think I'm going to give it n plus 1 total factorials. So yeah, from 0 factorial to n factorial. So the input here is going to be, or I could say parameters. We're going to have an integer n as an int, and then it's going to return a list of integers. And that list of integers is going to be a list of length n plus 1, where the kth element is k factorial. So the list needs to be a little bit longer because I'm going from 0 up to and including n, so I've got this extra element here. Okay, and then I need to be precise here. I don't want any negative inputs. I don't want any math people chiming in and saying that negative 14 factorial is e to the pi divided by the square root of 7. I don't need that. So we're going to raise a value error. And in this particular case, I'm going to say that the error is that the negative input given. Okay. And then otherwise, I'm going to say, well, this is a case of I know how many things are in my array. So I'm going to say, let's call it fact. And I'm going to say 0 times n plus 1. Okay. That will save us from doing something weird here if n is less than 0. And then way down here, I'm going to return fact. And then it's a matter of just ranging through and making sure every value is set appropriately. So the first one I want to set is fact of 0, and that's equal to 1. Okay. And then I want to range through and set k factorial. Here's where we get to use our fact that k factorial is k times k minus 1 factorial. Okay, so that's the previous thing that I just did. So I'm going to say for k is in the range of 1. We need to be careful here. We're going up to and including n. So we're going to go to n plus 1. Here's where I'm going to set fact of k is equal to fact of k minus 1 times k. And then at the end of that process, I return fact. So even though we've seen a new structure, we've now got lists in our life, everything that we're doing is the same thing that we've seen up to this point. We're just using the building blocks to do this n plus 1 times instead of just once. Okay, so now when I save this, what I would like to do is I can check this, right? So I will verify that this is working. Let's go to main. I don't think I have anything in main. I've got plenty of stuff in main. What am I saying? We're going to say In this particular case, I can say n is 10. I think I set n previously way up above, but it's fine. You can reset it to 10. And once n is 10, I'm going to say print factorial array of n. Okay, so what you're going to see, not negative, what you're going to see is when I run it, and I've commented out those troubling lines. So factorials up to n, and then r, something like that, just to make it a little bit more informative. So factorials up to 10 are 1, 1, 2, 6, etc., all the way up to this number. Great, so it's working. And the purpose of that was just to show you this is how a function works that returns a list. So a nice simple function doing something that we've kind of seen up till now. And now we get to come back and say, all right, let me show, like, I like taking my time with some of this because it allows me to show profile, like, what are the things that you could do to mess up, right? And we've talked about you could give a function the wrong input. But one of the things that I would say would be about as common of a beginner error as you could make would be to like have something that's off by one. One of the most, and I think in general, it's one of the most common type of errors you see in programming is errors that are off by one. So for example, what if I started that there, right? And it would be so easy to do because you could say, oh, well, I know how long the array is. I'm going to do this, or the list is. I'm going to do this for a number of values. So I could, in fact, I could just do this. I don't even need the 0. I'm just going to range everything up to and including n, not n plus 1. I know that, right? So I got that right. But this looks totally reasonable. I'm doing it for every element in the list. It's going from 0 to n plus 1, whether I add that 0 or not. And then but the question is, this is wrong. Why is it wrong? Question 1, why is this wrong? This is definitely bad. It's definitely a bad thing. But why is it bad? Why is this bad? Yeah, good. So when we go through the loop the first time, I try to set factorial, well, k is 0, fine, start of the loop. K is 0, and we're going to set fact of 0 is equal to k, which is 0, times fact of 0 minus 1. Now, people are telling me what should happen because I tried to set fact of 0 equal to fact of negative 1. So I'm trying to go off the side of the list. We know that the list starts at 0, index 0, and then it goes, can't go to the left of that, okay? And you say any language should have some kind of control set up here to prevent you from doing something like this. This is clearly the wrong thing and should be treated as such with an error. But that's not what's going to happen, is it? What is actually going to happen when I run this? What is actually going to happen? I should get an error. But that's not what's going to happen. Factorial of 0 would be 0. Why would it be such a thing? I thought factorial of negative 1 doesn't exist. All right, good. It's negative indexing. So you don't get an error. What you get is output that doesn't make any sense. That now I've got to dig into the program to even figure out like why this would have happened. Why are they all zeros? I can see the multiplication is happening. And it's because in this particular case, if k is 0, I've set fact of 0 equal to fact of negative 1 times k. And fact of negative 1 shouldn't exist. But we know, oh, what is fact of negative 1, right? Oh, that's fact of length of fact minus 1, which is the last element, right? oh, because that's very normal. This negative indexing thing, very useful, right? Except that what's happened here is we made what was clearly a mistake. And yet Python, by trying to hold our hand and help us out and give us all these bells and whistles, has not given us an error and has in fact given us this output that now I've got to figure out, what does this even mean? Like, what do you mean they're all zeros? I thought I set them to zeros, but then I did a bunch of things. And instead it went to the final element, which was set to be 0, and it did this multiplication. That's why I don't like negative indexing and think that it's just giving you this feature that at the end of the day, you don't need. Like, you can type out length of a minus 1. It's okay. For now, though, that's my Python hate du jour. And we want to move forward with working a little bit more with functions. And let me get rid of this bug so that I don't save that code and continue getting errors. But remember this, negative indexing does have some perils with it, and this does too. So preview, this can produce many nightmares also. But for now, what I want to do is I want to write another straightforward function so we can wrap up and get ready to implement primes. The function I want to write is going to be called minimum of an integer array, and it's going to take a list of integers. As input, I'm going to call that a, and then we're going to return an integer. I guess what this does, it takes a list of integers as input, and it returns their minimum. I'm going to save the doc string for now. Might add it here later. It's good code programming practice, but I want to just say, let's handle first, let's handle what happens if the length of that array is, or length of that list is 0. Then you should probably raise a value error and say there was an error here, and it's because empty list was given. Okay, that's nice because it means that if there's nothing in the list, I can't work with it. But now I know, for example, that there is a first element. So I can range over the whole list and I can be fine. And what I might do is to say, let's say m is equal to 0. This is going to store our minimum. Way down here, I'm going to return m. So this will store, this is our temporary variable to store our minimum. And then we're going to say, let's range over this list A. And I can go from 0 up to length of A. In order to do that, that's going to give me all the indices that I have. This is what's nice about zero-based indexing, is that we start with 0. We don't include length of A, but we go up to length of A minus 1. And you can see how many elements we range over because it's actually just this number minus this one. We'll say more about that later. For now, I'd point out you don't need the 0, so Python does have this nice little shorthand to say we're ranging over the length of A. And as I go through it, what do I want to say? I want to say, is the current value better than what I currently have? And if so, well, so I'm going to say, is it the case that A of I beats the current value that I have? And if it does, well, update M appropriately. So you think I'm ranging through the list. If I find anything that's smaller than what I'm currently storing, I'm going to set my value equal to it. It's a concept we'll come back to in a lot of different contexts and a lot of different types of applications, not just taking a minimum. What's the best thing? Store like some initial value and then go through the whole thing and see if you can beat it. So if that's the case, I've updated M. At the end of this, I know I've ranged through everybody in the list, and I can return M safely. Now this function, though, has a bug, which is what? What is our bug? It's not quite correct. Why is that? What is wrong with this? Looks reasonable. John says, why are we starting with m equals 0? Seems like a reasonable thing to do right now. What's the problem with starting with m equal to 0? I just said, let's set m as 0. That seems like a value to set. 0 could be bigger than our actual data, okay? Yeah, so that would be the case. So for example, if all your values were positive, you just set this harmless initial m value, and then every value in the list is positive, so nobody ever actually has this condition. It's never the case that a value in your list is less than m, so that's not good. And then the idea is how do you fix this? And there's a variety of ways to do it. One thing that we might do is just to grab the first one. And some people are saying you could just take the built-in Python function. Okay, good, right? But I'm trying to do something that's a little instructive to work with the start of things here. Okay, so we're going to say m is going to start at a of 0. And now that's going to allow this function to work. So if before, I can show an example here, but I'll go up to main and I'll say, let's set something that we know is going to be a problem, 3, 2, and 1. And then I'm going to print, in this particular case, I have min integer array of c. And I'm going to run this, and I get 1. Okay, so that's the final thing that I see printed. I will show you if I had set this to 0, we'd have been in trouble, because it's never the case that any value is smaller than 0 as we go through it, so that's a bad thing to do. So I'll restore this for now. I'm also going to show you one little quick shorthand ranging technique, which is I could range over all the elements in the list like this, but actually I don't care about I. I is really like not that relevant. So in this particular case, what do I care about? I care about the values. And I will just show you that this is, again, the sort of thing you're fine writing your for loops like this, but there's a little trick to say for val in A. That will range over all of the values in A, and now I can say we test the current value against m, and if it beats m, then m is equal to value. So that's one way of making this function a little bit shorter. One other thing I guess we could do is I could have set this equal to an initial value, but then as I range through it, I would have needed to check, are we at the first value? So I like where we are here. I like this. The lesson though here is you can do it this way, you can do it the way I showed before. It's always better to do one thing well than a bunch of things poorly. Python's a good example of that. It gives you so many ways of doing many things, but in a lot of the cases, you just need one. One more thing I want to do, actually like 2 more quick things to discuss. One is variadic functions. So part of the reason why I introduced this is you've already seen a variadic function. So in Python, we're going to write a function that's built in, which is essentially min. So min in Python can take an arbitrary number of inputs. So like min of 2, 3 works, but min of -1, 47, 68, and 900, that works too. You can give it however many things you like. We've not seen functions that work like that, and I want to show how that works. Say I wanted to write a function called like minimum integers, and minimum integers was going to take an arbitrary number of things. How you indicate that, and we'll come back to this in the class, is to say star, and we're going to have a parameter called whatever we call it. In this particular case, I'm going to call it numbers. So I'm going to say star numbers indicates that we can have an arbitrary number of inputs. Okay, so what is star numbers? I'm going to say :int, and it's going to go to an int. So this means it's an arbitrary collection of this. It could be one thing, it could be a million things. And what happens behind the scenes is numbers is a tuple. Okay, so we get to use tuples again. And we might say, all right, well, if the length of numbers is equal to 0, this means that the user didn't give us anything. So I need to raise a value error. And that value error says no values given to function. That's not good. Otherwise, if we make it here, we could say, well, m is equal to numbers of 0. And then for val and numbers, we're going to say if val is less than m, m is equal to val, and then at the end of this whole process, I'm going to return m, and you think you went through that really fast, right? How'd you do that? And it's because my memory's not so bad that I don't remember that I just wrote this function. And the lesson here is if you're ever writing code and you think, gosh, that's similar, I've just done this, this comes from another place, there's always something that we need to do when you start seeing code that gets duplicated. Does anybody know what it is? What do we do? High-level programming lesson here. When you start seeing code that's the same as what you've done before. As a refresher, if you're curious, can you index tuples? Yes, you can access values. You just can't change them. You can't do something like numbers of 0 equals blah. That won't work. Okay, but you can go in and access any value of a tuple you like. Create a common function. Good. The fancy word is subroutine. So when you start seeing redundant code that's in multiple places, that all can be put into one place, and then you just call that function again. In particular, I don't need to write any of this. I don't need to do this. I just need to say, let's use the function that we already wrote. So in this particular case, it might be nice to say, well, numbers is a tuple. I just wrote a function that's going to work with basically a tuple. It's going to work with an array. Why don't I just call, say, m equals min integer array of numbers, and then return m. I could even do this in one line, right? Use the function that I've already written. It's got error handling. It's got all that good stuff. There's no reason to write all this code again. Write it once, make sure it's correct once, and then use it anywhere you need it. So the lesson there that we will see is don't rewrite code if you can just use a subroutine. And there's one issue here, which is that, okay, technically, there's a little bit of a type issue here, which is that numbers is a tuple, but this takes a list. So Python will be a little strict here. We can handle this just by saying convert it to a list. So we have a built-in function that will do that for us. All right, and now I'll show you if we call this in main. Go to main, and we say, let's say the minimum of 3, 4, and -7 is, and I'll say min integers of 3, 4, -7. It'll take as many inputs as you like. You see it's going to give us the correct answer. Pretty good. Pretty good. One more point. So again, we're going to use that over and over again. Anytime I can use a subroutine, I'm going to use a subroutine. One more point. This will allow us to recall some things that we've learned previously in the course, which is I'm going to create a function called, put it down here at the bottom. Doesn't matter where I put it. Okay. Change first element, and it's going to take a list of integers, and it's not going to return anything, and I'm a little lazy just because I want to polish this up and get to prime, so I'm not writing a doc string here, but all I'm going to do is set a of 0 is equal to 1, okay, and I should say if length of a is equal to 0, okay, raise value error. Bad. All right. The only thing I'm doing, though, is setting a of 0 equal to 1. Then I'm going to go into main, and I'm going to create a list. Okay. And I have this list. We can rename C. Okay. So I'm going to set C to now it's going to be 0 times 6 copies of 0. And I'm going to call change first element of C, and then I'm going to print C. My question is, what happens? And there's not a lot of possibilities for what could happen. I'll promise you there's not going to be an error. All right, so I've set C to be this list that's 6 copies of 0. And then I called this function that sets C of 0 sets the initial element equal to 1. My question is, what gets printed? What do we know up till now about things that get passed into functions? In the meantime, I'm going to say there's disagreement. Some people think that the first element here is going to be a 1. Others think it's going to be a 0. The question is, what happens? There's only one way to find out. It's to run it. We see that it does change. This is different from everything that we've learned about Python up to this point. Up to this point, what happens is, if I passed something into a function, we've seen this in a previous code along. If I pass something as a parameter into a function, I create a copy of that. And then that copy is what gets changed. There's an example from a previous code along. Go find it. If I work with an integer or a string or a Boolean variable, or any of these, or float, any of these basic types, if I pass that into a function, Python says, oh, I'll create a copy of that for you. And if you change that copy, that's fine, but it's not going to change the thing that you passed into the function. This is different. So what is happening here is that lists are not the fancy term, Claudia got it, passed by value. Integers are, right? Strings are, etc. So integers, strings, floats, all these other built-in type variables are passed by value. Copy is created when they go into a function. Lists are not passed by value, they are passed by reference, okay? So you die in the function, you die in real life, okay? It's a dark way of putting it, but you have access to whatever you pass into that function. And we see an example of it here. I pass C into this function, and what does the function do? It actually, you can see it's calling C something different, right? The parameter here is called A. All it does is set the initial value to 1, and then the function finishes. So when we pass C into this function, you're getting access to be able to actually change the list. We're going to understand a little bit more about what's going on here later, okay? Which is that lists are passed by reference, so you can change them in functions, but other types aren't. It turns out there's one explanation that is going to explain all of this. And frankly, I know I can have Python hate in my heart at some times. It's actually something that I think is really neat about Python, but we're going to need a lot more understanding in order to see it. We're going to need a transition to object-oriented programming. There's going to be one answer that you're going to think, oh, I understand the whole thing now. But we'll have to save that for another time. For now, we're ready to turn our attention back to prime finding and start learning how to find primes in the first place, then learn how Eratosthenes came up with this beautiful prime finding algorithm from over 2 millennia ago for finding them faster. And then we want to do something like, let's see how many primes there are up to a certain point and graph it and make pretty visuals of all this, which is going to require that we understand a little bit about how to visualize things in Python 2. But that's it for now. That's our work for next time. In the meantime, please always like us, subscribe, join our Discord, become a member, hang out with us, join the movement, and I'll see you next time. Happy coding.